Welcome to this explainer. You know, it's really easy to look at a mountain or a valley and just see static rock, right? Dirt that's just sitting there. But today, we're going to look at the ground beneath our feet a bit differently. Because the surface of our planet, it's actually the exhaust of this massive dynamic engine churning right below us. We've got exogenic processes working on the outside and endogenic processes working on the inside, constantly shaping our world. So to really understand why the Earth shakes or why a volcano suddenly erupts, well, we have to look inward. But that brings us to the ultimate geological mystery. If we can't actually dig down past the very outermost crust, how do we actually know what's inside our planet? It's not like we can just book a journey to the center of the Earth to collect some samples, right? So our knowledge actually comes from clever clues, making inferences, and decoding the signals the planet is constantly sending us. It's a fascinating puzzle, and today we're going to solve it together. Section 1, Investigating Earth's Hidden Depths. So let's dive into this. Just how deep into this planetary engine have humans actually managed to go? Well, look at this massive number, 6,378 kilometers. That right there is the radius of the Earth. If you wanted to get to the absolute center, that's the exact distance you'd have to travel. That is a lot of rock, magma, and metal between us and the core. Now contrast that massive 6,000 plus kilometer radius with 12 kilometers. Yeah, just 12. Through projects like the Deep Ocean Drilling Project, the absolute deepest drill hole humans have ever created, over at Kola in the Arctic Ocean, reaches just 12 kilometers down. To put that into perspective, those famous super deep gold mines down in South Africa, they only go about 3 to 4 kilometers deep. And why do they stop there? Well, because it literally becomes unbearably hot. We physically cannot go any further. So if our direct reach is a tiny 12 kilometers out of over 6,000, we obviously need other ways to look inside.
And that brings us to how we actually gather our evidence. We divide it into direct and indirect sources. Direct sources are the things we can literally touch, surface rocks, samples from those deep mines and ocean drills, and the molten magma that volcanoes kindly spit up to the surface for us to test in the lab. But honestly, the real magic happens with the indirect sources. Scientists measure how temperature, pressure, and density all increase the deeper you go. They also look at gravity anomalies. Because, fun fact, gravity is actually stronger at the poles than at the equator, and it changes based on the mass of the material hiding down in the crust. But here's my favorite part. One of our absolute best indirect sources comes from space. Meteors. They act like a geological cheat code. Since they're built from the exact same planetary building blocks as Earth, analyzing a meteor is basically like reading a raw ingredient list for our own planet's interior. But while meteors and gravity are super useful, there's one indirect source that acts as the master key.
Section 2, Anatomy of an Earthquake. To understand how earthquakes act as a diagnostic tool, we first have to look at the immense physical forces at play. Basically, an earthquake is a massive release of energy along a fault line, which is just a sharp break in the crustal rocks. Picture rock strata pressing hard against each other, but friction locks them tightly in place. They really want to move apart, so deformation just slowly builds up as the pressure mounts. And then finally, the tension completely overcomes the friction, the blocks abruptly snap and slide past one another, and boom, a massive wave of energy is released in all directions. Now, that specific, deep, internal trigger point where the rock finally gives way, that's called the focus, or the hypocenter. All of that incredibly intense, pent-up energy starts radiating outward from this spot, deep underground, traveling right through the body of the Earth. And this brilliantly illustrates how that deep subterranean energy actually translates to the surface and to our daily lives. The epicenter. This is the exact point on the Earth's surface directly above the hypocenter. Since it's the closest surface point to that deep release of energy, it is the very first place to experience the waves. So when you hear about an earthquake on the news, they're giving you the location of the epicenter, but the actual violent engine that started the whole thing was the hypocenter, way down below. All right, let's talk about the waves themselves, because they are effectively the ultimate geological ultrasound. Body waves are generated at the focus, and they come in two main flavors, P waves and S waves. P waves, or primary waves, are the fast ones. They're actually a lot like sound waves. They push and pull, squeezing the material as they go, and they can travel through gas, liquid, and solid, no problem. But S waves, secondary waves, are completely different. They arrive a bit later, vibrating perpendicular to their direction, creating these crests and troughs. Now, here's the absolute most important fact in this entire explainer. S waves can only travel through solid materials. If they hit a liquid, they just stop, dead in their tracks. Keep that in the back of your mind because it's the absolute master key to this whole planetary puzzle. But before we solve that deep Earth mystery, we should probably anchor all this abstract physics to real human stakes. Because when those deep body waves finally hit the surface rocks, they generate surface waves, and those are actually the ones that do the damage. You'll see massive landform changes like ground settlement, mudslides, and soil liquefaction. Not to mention the immediate human hazards, structural collapse, fires, and even tsunamis. Now, earthquakes are measured by magnitude, which is the total energy released on the Richter scale. Tiny quakes happen literally all the time, but thankfully, high-magnitude quakes of 8 or above are incredibly rare. Section 3. Decoding the shadow zones. So, what happens when our geological ultrasound waves just go missing? We have seismographers, these highly sensitive instruments, set up all over the globe, constantly listening for earthquake waves. But scientists stumbled onto a really baffling mystery. For every single earthquake, there is a specific dead space on the far side of the planet, sitting between 105 degrees and 145 degrees away from the epicenter. Inside this zone, the seismographers record absolutely nothing. No P waves, no S waves. Complete silence. This happens because the materials deep inside the Earth have different densities, which actually causes the waves to bend or refract, leaving a distinct shadow. But what's really wild here is the sheer scale of the S-wave shadow zone. See, P waves do eventually pop back up once you get past 145 degrees, but S waves, they never do. The entire zone beyond 105 degrees does not receive a single S wave. That is a little over 40% of the Earth's entire surface. Remember our golden rule about S waves from earlier? They cannot travel through liquid. So because this massive 40% blind spot exists, it absolutely proved to scientists, without a doubt, that deep within the Earth, there has to be a massive layer of liquid blocking those waves from passing through. Section 4. Layers of the Earth. By mapping exactly how these waves bend, or where they stop altogether, scientists successfully mapped out our planet's entire internal anatomy. Let's start at the outside with the solid layer, the brittle crust. But notice the immense variation in thickness here. The oceanic crust, the part under our oceans, is actually incredibly thin, averaging just 5 kilometers. But the continental crust, the land we actually live on, averages about 30 kilometers. And it gets even crazier where you have major mountain systems pushing the Earth up, because the crust actually drops way down to support all that weight. In the Himalayan region, the crust is a massive 70 kilometers thick. Right beneath the crust is the mantle, extending down to a depth of 2,900 kilometers. Now, the crucial point here is the upper portion of this mantle, known as the Asthenosphere, a word that literally means weak. Extending down about 400 kilometers, this weak, magma-rich zone is the primary engine feeding molten rock straight up to our surface volcanoes. Finally, we reach the core. Thanks to those S-wave shadow zones we just talked about, we know for a fact the outer core is liquid. Meanwhile, the immense crushing pressure keeps the inner core totally solid. This core is incredibly dense, made up of heavy materials, primarily nickel and iron, which is why geologists sometimes call it the NIFE layer. Section 5. Volcanoes and fiery landforms. So, we've got this intense internal engine, a brittle crust, a swirling mantle, and a heavy, scorching iron core. When magma from that engine finally breaches the surface, we call it lava. And the volcanoes it creates, they have distinctly different personalities. Shield volcanoes, like the ones in Hawaii, erupt very fluid basalt, so they spread out nice and wide. Composite volcanoes are your classic, steep, layered mountains that shoot out cooler, sticky lava and ash. Then you've got calderas. These are so incredibly explosive that when they erupt, they literally just collapse in on themselves, creating a dramatic, deep depression. We also have flood basalt provinces that pour huge amounts of fluid lava over vast expanses of land, and mid-ocean ridge volcanoes, forming a mind-blowing 70,000-kilometer chain right under the sea. But, we can't forget that so much of the real geological action happens entirely out of sight. Not all magma actually erupts. A ton of it just gets trapped inside the crust and cools into igneous rocks, creating what we call intrusive forms. Giant, cooled magma chambers turn into these massive underground domes called batholiths. We also see pipe-fed domal structures known as laccoliths. Magma that squeezes horizontally forms flat sheets called sills, while magma that cools vertically inside cracks forms these huge wall-like dikes. These hidden structures literally shape huge expanses of our land from the inside out. For instance, the beautiful domal hills of the Carnatic Plateau are classic examples of these hidden laccoliths and batholiths, and dikes were the very feeders that built the massive Deccan traps in India. Which brings us to our final thought for this explainer. The Earth is not just a static rock floating in space. It is a continuously shifting, deeply layered machine of pressure, magma, and iron that uses volcanoes as its pressure valves. Knowing that a massive, dynamic engine is churning right below your feet, blocked only by a thin crust, how will you look at the landscape around you tomorrow? Will you just see dirt and hills, or will you see the exhaust of the geological engine we call home? Thanks for exploring the depths with me today, and hey, keep questioning the world beneath your feet.